So now the process is shown on TS diagram. As you can easily see that you have two pressures here. Let us say that this is pH or okay, P2 and this is P1, and this P is constant. So P2 is equal to P3, and this is again an isobar. So P1 is equal to P4, okay, and P2 is greater than obviously P1, right. So process 1 to 2 is isentropic compression, so it is a vertical line. Process 2 to 3 is isobaric heat rejection, that means along the constant pressure line, and during this process you can see that the temperature of the air drops from T2 to T3, and process 3 to 4 is isentropic expansion in the turbine, okay. So it is again a vertical line, and process 4 to 1 is again isobaric heat extraction from the heat source. That means basically you have heat extraction from the low temperature heat source and heat rejection at this point, okay. And as you know, if you are using it for cooling, this is our required cooling output, okay. Now we can quickly write the equations for various processes. For example, process 1 to 2, what we are doing is we are simply applying the steady flow energy equation. We are neglecting changes in kinetic and potential energies, okay. So these are the two assumptions. Apart from that, we are following the cold air standard cycle analysis, okay, that you must keep in mind always for this lecture, okay. So for process 1 to 2 is isentropic compression, so there is no heat transfer, only work transfer takes place. So this is the work input to the compressor. This is simply equal to mass flow rate of the air into H2 minus H1. This is the enthalpy change during the compression process, okay. So m dot into H2 minus H1. So H2 minus H1 is written as Cp into T2 minus T1, where Cp is the specific heat, T2 and T1 are the final and initial temperatures for the compressor, okay. And process 2 to 3, if you remember, is isobaric heat rejection, okay. During this process there is no work done, that means there is no work transfer during this process, okay. So W23 is 0 because this process was performed in a heat exchanger, so no work was done. So when this is 0 and when again delta Ke and delta Pe are negligible, if you are applying steady flow energy equation, you can easily show that Q2 to 3 is m dot into H2 minus H3, which is equal to m dot Cp into T2 minus T3. And process 3 to 4 is isentropic expansion, so Q dot 3 to 4 is 0, okay. So W3 to 4 is Q m dot into H3 minus H4, which is equal to m dot Cp into T3 minus T4. And finally process 4 to 1, again work is 0 during this process, and it is isobaric heat rejection, so you can write this as m dot into H1 minus H4, which is equal to m dot Cp into T1 minus T4. Again for the process 1 to 2, you can get this equation very easily, as I was mentioning in the little while ago. You can get this expression. How do you get it? We can write PV is RT and P1 V1 to the power of gamma is P2 V2 to the power of gamma, okay. So if you are using these two equations, you can arrive at this expression, okay. So what it shows is the exit temperature of the compressor is equal to the inlet temperature multiplied by the pressure ratio to the power of gamma minus 1 by gamma, where gamma, as you know, is Cp by Cv, okay. I am writing this as T1 into Rp to the power of gamma minus 1 by gamma, where Rp is equal to P2 by P1. So this is called as pressure ratio. We have only two pressures in this cycle, so this is the pressure ratio, okay. Similar to the process 1 to 2, process 3 to 4. Process 3 to 4 is isentropic expansion. So again you can get this equation for the process 3 to 4, where T3 is equal to T4 into P3 by P4 to the power of gamma minus 1 by gamma, which is again equal to T4 into pressure ratio to the power of gamma minus 1 by gamma, okay. So from these two relations you can very easily show that T2 by T1 is equal to T3 by T4, okay. And now we apply the first law of thermodynamics for the entire cycle. So as you know, cyclic integral of del Q is equal to cyclic integral of del W, and heat transfer took place in two processes, 4 to 1 and 2 to 3, and this is positive because it is taking heat from the heat source. So for Q4 to 1 is positive, it is rejecting heat, so Q2 to 3 is negative, okay. And there are two work transfer processes, process 3 to 4, that is the isentropic expansion in the turbine. It is positive because system is doing the work, and this is the work input to the compressor. It is negative because you are supplying the work to the system, okay. and this thing is equal to W net, right. So finally you find the W net is equal to Q4 minus Q4 to 1 minus Q2 to 3. So COP again we are defining as Q4 to 1 divided by W net. So you can very easily show that this is equal to T1 minus T4 divided by T2 minus T1 minus T3 minus T4, and this we can easily show, because as I said you can write this expression T2 by T1 we have just now shown is equal to T3 by T4. So if you are using this expression here, you can arrive at this equation, okay. And you can also write COP in terms of pressure ratios, okay. So again the relation, you remember the relation I have shown just now. So ultimately you can express COP in terms of pressure ratios and gamma, okay. So finally the COP of the ideal reverse Brayton cycle becomes a function of the pressure ratio, and it is very easy to show that COP reduces as pressure ratio increases, okay. That means higher the pressure ratio, smaller will be the COP, okay. So these are the typical equations, and it is very easy to derive these equations on your own. All that you have to do is take each component and apply steady flow energy equation to the component, okay, and assume the Cp to be constant, neglect kinetic and potential energy changes, and apply steady, as I said, steady flow energy equation to all the components, okay. Right. So we have seen that this is I have already mentioned, the two isothermal heat transfer processes are replaced by two isobaric heat transfer processes, and for the same heat exchanger terminal temperatures you can very easily show that the COP of a reverse Carnot cycle is always greater than the COP of a Brayton cycle, okay. Let me show this. Okay. Right, I will show this a blank sheet. Okay. So what I am showing here is the reverse Brayton cycle 1, 2, 3, 4, right. So you have two isobaric processes here, okay. Process 2 to 3 and 4 to 1 are isobaric processes, process 1 to 2 and 3 4 are isentropic processes, okay. And if I am fixing the terminal temperature of hot and cold heat exchanger, that means if I am fixing temperature at point 1 and temperature at point 3, then 1, 2 dash, 3, 4 dash will be a Carnot cycle which has the same terminal heat exchanger temperature as that of a reversed Brayton cycle, okay, right. So now for the reverse Brayton cycle, just now we have shown that the efficiency is given by T4 divided by T3 minus T4, that means this temperature divided by this temperature minus this temperature, okay. What is the COP of the Carnot cycle? COP of the Carnot cycle is obviously depending upon these two temperatures, okay, TH and TL. Here TH and TL are nothing but T3 and T1. So Carnot cycle COP is given by T1 divided by T3 minus T1, okay. So this will always be lower than this. Why? Because T4 is always lower than T1, okay. T4 is always less than T1. As a result, COP of the Brayton cycle will always be less than the COP of a reverse Carnot cycle, okay. Now let us look at actual reverse Brayton cycle. Whatever we have been discussing so far is an ideal cycle. So the actual cycle differs from ideal cycle due to two reasons. The first reason is the non-isentropic compression and expansion processes. That means basically the process 1 to 2 and 3 to 4 could be adiabatic, but they will be definitely irreversible. That means there will be some irreversibility maybe due to fluid friction, okay. So the process becomes non-isentropic. This is the first difference between the ideal cycle and the actual cycle. And the second difference is we have neglected all the pressure drops in the cold and hot heat exchangers. Typically when a fluid flows through a heat exchanger consisting of long lengths of tubes, there will be fluid friction and pressure drops, okay. In the ideal cycle we consider that there are no pressure drops, so you have only two pressures, whereas in actual cycle there will be pressure drops right. So these are the two reasons why actual cycle differs from an ideal cycle. I can show this thing on a, so you can see the difference here. Here 1, 2, 3, 4, 1, 2, 3, 4 is the ideal cycle, okay, and 1, 2 dash 3, 4 dash, this is 0.4 dash, okay. So 1, 2 dash 3, 4 dash is the actual cycle, okay. So you can see that, for example, process 1 to 2, in the ideal cycle it is an isentropic process, okay. In the actual cycle it is non-isentropic, okay. That means entropy increases during the process because of the irreversibilities. That means you will find that entropy at point 2 S2 dash will be greater than S1, whereas S2 is equal to S1, okay. So this is one difference. So what is the consequence of this difference? You will find that temperature T2 dash will be larger than temperature T2, okay. Because of the irreversibility, you find that exit temperature is higher compared to the ideal isentropic process, okay. And process 2 to 3, in actual this should have been point 2 should have been here, okay, and the heat rejection should have taken place ideally along a constant pressure line, but you will find that because of fluid friction there is a pressure drop here, okay. So you find that there is a reduction in pressure during the heat rejection process. Similarly, process 3 to 4, entropy remains constant if it is an ideal process, but in an actual process again entropy increases, so S4 dash will be greater than S3, okay. So the process is something like this. So as a result you have a cycle 1, 2 dash, 3 dash, 4 dash in an actual case. What is the consequence of this? You can very easily show that the consequence of this is a reduction in the COP, okay. The COP reduces because of two reasons. First reason is that your cooling effect is reduced, because in an isentropic process, isentropic expansion process, the temperature should have been 4, but because of the irreversibility now the temperature is 4 dash, okay. So T4 dash is greater than T4, okay, and your useful refrigeration effect QL is m dot Cp into T1 minus T4 dash in case of an actual cycle, right, and in case of an ideal cycle this will be T1 minus T4. Since T4 is lower than T4 dash, obviously QL in actual case will be smaller, okay. And we can also define the actual work of compression and actual work of turbine by defining isentropic efficiencies, okay. For example, the actual work input to the compressor during the process 1 to 2 is defined as the isentropic work divided by the isentropic efficiency, okay. So you can see that typically this isentropic efficiency of the compressor will always be less than 1. That means W12 actual will always be greater than W122 isentropic, okay. So the required work input increases because of the irreversibility, right. And the next process, that is isentropic expansion in the turbine, the work output of the turbine now gets reduced because of the inefficiency, okay. And here again we define an isentropic efficiency for the turbine, okay. Again this is lower than 1, so the work output of the turbine will be lower than the work output of the ideal turbine, okay. So the net result is that W net in an actual case will be much larger than W net of ideal case, because output is reducing and input is increasing, okay. And you can easily write the isentropic efficiency for the compressor in terms of the enthalpies, okay. You let's look at the earlier diagram. So it is defined as the actual and the enthalpy change divided by the enthalpy change for an isentropic process, okay. And this can be written in terms of temperatures, because we are assuming the Cp to be constant. So isentropic efficiency of the compressor is written as T2 minus T1 divided by T2 dash minus T1, and if you remember T2 was greater than T2 dash, okay. So obviously this isentropic efficiency will be I am sorry, I think it is the other this thing other way. T2 is actually lower because T2 dash is for the isentropic process, okay. So this will be greater than 1, right. And for the turbine also you can write the efficiency in terms of the temperatures, okay. again this will be less than 1, okay, because as you have seen the actual temperature at the exit of the turbine will be higher than the temperature in an isentropic process, okay. So, as a result, as I said just now, the net work input increases. Right. So, we find that COP of actual reverse Brayton cycles will be considerably lower than the ideal cycle because of these two effects, reduction in the cooling output and increase in the net work input. In fact, the reduction could be quite considerable depending upon the design, and one way of improving the system performance is to design efficient compressors and turbines. Actually, this is a very critical issue, okay. So, if you want to have a good efficiency, you must have efficient compressors and turbines. Now, Brayton cycles can be open or closed, okay. So far we have discussed a closed cycle, okay, that means the same amount of air is flowing through the cycle repeatedly, but in actual case you can have a open cycle or a closed cycle. So, let us see what is an open cycle. In open systems, cold air at the exit of the turbine flows into the cold space and cold heat exchanger does not exist. That means what we do in an open system is air from the turbine is directly released into the cold space. For example, if you are using it for an aircraft cooling, you directly release the cold air into the cabin of the aircraft, okay. So, the air gets heated up as it picks the heat from the cabin, okay, and then you take the air and send it to the compressor, okay. So, you really do not have a low temperature heat exchanger, okay. So, this is an open system, right, and there is no guarantee that the same air is flowing through the compressor, okay. The advantage of this system is obviously its simplicity, and since you do not have a cold heat exchanger, the total weight of the system will be reduced considerably, okay. That is the reason why we use this in aircraft cooling, okay. And second characteristic is typically the low side pressure will be atmospheric. When you are releasing the air into an occupied space, typically occupied space pressure should be close to the atmospheric. So, the low side pressure also has to be close to the atmospheric, okay. So, these are the two characteristics of open systems. As against this open system, in a closed system we have two heat exchangers, the high temperature heat exchanger and a low temperature heat exchanger, and the air of the system does not get mixed with the outside air. That means the same air flows through the cycle repeatedly. And one advantage of this system is that you can have low side pressure higher than the atmospheric, okay. Such a cycle is known as dense air system. That means you can operate your low side pressure at pressures much higher than the atmospheric, typically 3 to 4 bar, okay. That means the air will be quite dense, okay. So, you call these systems as dense air cycles. What is the advantage of dense air cycles? As you know, as you are increasing the pressure, the density increases, specific volume reduces, and for the same mass flow rate, the amount of volume that you have to handle will be reduced considerably, okay. So, that means volumetric flow rate of air reduces considerably. So, this will give you a lot of savings in terms of heat exchanger sizes, compressor sizes, etc. Okay. So, this is the advantage of dense air cycles, okay. So, dense air cycles are obviously possible only with closed cycle systems, and you can also use gases other than air. For example, if you have a closed cycle system, it is not necessary that you have to use air only, okay. You can also use other gases such as helium or any other gas, okay. Such systems exist for other applications other than aircraft cooling, okay. Typically in aircraft cooling we use air, so and normally it will be open, okay. Now let us look at aircraft cooling systems. So, why do we need first of all air conditioning or cooling in an aircraft? We know that as you go up, typically aircraft will be flowing at very high altitudes. It could be as high as let us say 10 kilometers or even more. So, as you know that as you go up, the temperature and pressure both reduce. In fact, at an altitude of 10 kilometers, the outside temperature can be as low as minus 30 or minus 40 degrees centigrade, okay. When the outside temperature is so low, why do you need a cooling system? Maybe you may be thinking that you require a heating system, because outside temperature is very low and the required comfort temperature is about 21 degrees or so, right. So, there is a large temperature difference between the inside and outside, okay. So, if at all there is any heat transfer, it should take place from the inside to the outside. That means you require a heating system, not a cooling system. But you find that in actual practice we need a cooling system, not a heating system when the aircraft is flying at high altitudes. This is because of the following reasons, okay. The first reason is that there will be large internal heat generation. Okay. So, typically in an aircraft there will be a lot of heat generation because